Well, good morning to everyone. As Helen said, I'm trying to get you through my quest for understanding modern amplification systems. I wrote there amplifier systems, amplification systems, the same thing. You will see that I might change between the two terms. First of all, I would like to thank all the manufacturers involved in this, for making possible this investigation, and also to my colleagues from ISCEx for dealing with trying to pass my workload to them while I was doing this investigation. So thank you to all of you. So as Helen said, this is nothing new. This is a more extended investigation and revised investigation from the one that I previously presented in ISCEx 2017. We call it digital amplifiers. Are they too well designed? Well, what is different from this investigation is, or why we revised the investigation, the previous investigation, is we have now a new approach. We are looking the systems not as an amplifiers, we look them as systems, like cores, amplification systems, all of that in once. And we look them through if it was a black box, so input, what we have output, that's what we're going to present. We extend the range of systems. Now we have 10 different systems from 8 different manufacturers. We have we have reduced the amount of signals that we have used for the measurements. Now we are only using the 1 kHz sine wave, the well-known STIPA signal, and a speech track. And we extend as well the scope to non-EM54 certified systems. I said that this started in 2017. Well, actually, this is even started earlier. After the 2017 presentations, John Rawlings approached us, and he mentioned that he had a conversation about the headroom assumed during the modeling stage and the real headroom of the amplification systems. That conversation happened between him and Peter Barnett in a mass transport project in London, the Jubilee Line extension, 25 years ago. So what I mean, this is nothing new. This is something that has been around for years. That project was delivered successfully because back in those days, the amplification systems, they were more forgiving, so we could have more than what it said on the spreadsheet. Before going into the data, I think it would be interesting to put some characteristics of voice alarm systems. Well, voice alarms, SSEP, ISCEx systems, the main object of these systems are to be intelligible. So to have or to achieve that required intelligibility, most of the time we require to have high SPLs. That means that we want to squeeze the system as much as possible, not just in terms of power consumption. Is power consumption the space that the equipment will take into the technical room, the battery backup, the cooling system for that room, all of that at the end is what it gives that efficiency. So that's why these systems, they're usually driven to the creeping threshold. Also, what these systems, they are driven in what we call all-call, so all the zones are going to be active at one point. And also the systems, they work at what is called constant voltage. It's not constant voltage, but it's 70 or 100 volts. All the measurements that we carry, that we did with these systems, they were done with the systems configured to work in 100 volts. And if possible, fully loaded to replicate the all-call scenario that I'm talking about here. Then we found some interesting, well, I put relevant clauses. It's only one, but we think that is quite interesting. According to EM54 part 16, this clause is talking about measuring the rating power of the amplification systems. And it's more or less, our interpretation is that in a frame, in a chassis, for example, that we have 4 channels, not all the channels have to be fully loaded to the maximum capacity. Only one has to be fully loaded to the maximum capacity to do the rating test. That kind of conflicts a little bit with the potential all-call scenario where all the channels of that amplification system will be fully loaded. So I'm going to try to get you through this crest factor visualization. Hopefully it will not be really messy. I will try to do my best, but I'm going to plot here bars representing the crest factor of the signals. The bottom of the graph will represent the VRMS value, and the top of the graph will be the peaks of the signal. As you can see, well, we have like full power, 100 volts, and then we have different power ratios. So the first signal that I'm going to put is like the sine wave. It's a 3 dB crest factor signal. In amplification systems, we expect to achieve 100 volts. So the minimum headroom required in those amplification systems is 3 dBs. And we are going to assume for the other signal that that's the limit of these amplification systems. So when we have a steeper signal that is a 14 dB crest factor, we can see that the peaks, they will be of that plus 3 dBs, but the RMS of the signal would be at 1/13 power. Okay? That's with the minimum required headroom again. Some amplification systems might have more headroom, so that bottom of the graph will go up. The steeper signal is used to measure STI using a direct method. If we want to use an indirect method, we use a speed-shaped noise signal. This is effectively like a pink noise signal, but with a different shape. Okay? Has a lower crest factor, 12 dB crest factor. Then we have this speech track signal. This has a 15 dB crest factor signal. The reason why it has a 15 dB crest factor signal, it's going to come a little bit later, so just bear with me on that one for a bit. We use this signal to carry out our measurements. And then we have this allowed for voice alarm speech. This 11 dB crest factor signal is coming from an internal investigation in AMS acoustics that is the maximum or the lowest crest factor that we can have in a speech track before having noticeable clipping or noticeable distortion. And that's what we assume that was acceptable for voice alarm applications. So do you remember that I said like about the 15 dB crest factor? Well, in 60268, part 16, there is a 3 dB adjustment that it has to be made in the speech tracks. And that's to compensate for the different intelligibility when measuring STI using artificial signals or when using speech tracks, like proper speech. So when using an indirect method, the speech-shaped noise, as you can see, the speech track, that signal will correspond to a 15 dB crest factor speech track. Okay? If we wanted to use that 11 dBs, all the steeper and the speech-shaped noise signals would need to be 3 dB, the bottom of the graph would need to be 3 dB higher than this line. So all the signals would need to be, all of this bottom of the graph would need to be up here. That means either the amplification system have more headroom, so the red line goes up, or the signals are crunched. There are no other ways to do that. So just to summarize this, we use the 1K sine wave to do the rating. We use the steeper or the speech-shaped noise to measure STI. And then, at the end of the day, these two signals, or whatever, like depending on the crest factor, is what is going to be played and what is going to be reproduced by these amplification systems once they are used on a real emergency. So let's go into the results. Well, the first thing we said, like, let's see how these amplification systems, they correspond the rating, what is on the specs and what we measure. We would expect all the systems to achieve the dotted line, the full power, the 100 volts. Again, as I said, the values that are going to be plotted here represents the bottom of this bar. Well, first system doesn't achieve 100 volts. This system, as you can see, doesn't get flat, doesn't get nonlinear. This system had a time-dependent voltage, so after a second, it couldn't maintain for more than a second the output voltage. It dropped the voltage. That's called like burst mode. In different manufacturers, they call them different, but well, That's, I think, the general term. So we couldn't achieve 100 volts with this system for longer than a second. You will see that wobbly thing. That's because of the resolution of the sound. We measure all of this using a sound level meter. It had a resolution of 0.1 dBs. So that wobbling thing that you are going to see in all the graphs is the resolution of the measurement method. Then we have this system. This system, believe it or not, is the same system. The gray graph is when it's only one channel loaded, and the brown graph is when it's fully loaded. So that system had a 3 dB drop when the system is fully loaded. And it doesn't achieve 100 volts once it's fully loaded. Then we have this system. I don't know if you can see it. That system, it does exactly what it has to do. Goes to 100 volts, achieve 100 volts, get flat. Nothing more, nothing less. We have then all of these 4 systems. They do a little bit more, a little bit less, more headroom, less headroom. Then we have this system, more headroom than the other ones, and it has a smooth transition to the 100 volts. It doesn't get like at one point and then nonlinear. It has kind of like a smooth transition to the nonlinear region. And then we have these 2 systems that they exceed quite a lot the 100 volts in the linear region. The dark blue, the top one, gets nonlinear because we measured the systems until they got nonlinear, or we had some alarms in the software showing that the system temperature alarms or the system shut down, or like what happened in the blue one, it started to have a smoke coming from the back of the amplification system. So we decided that that was not good enough to keep going pushing that one. So we follow kind of like those 3 indications. To be fair, that was the only system that had that problem, and it's not a modern amplification system. It's a 30+ old amplification system. So if we saw that kind of like a big range of behavior with the 1 kilohertz sine wave, that is the stable signal, let's see what happened with the STEPA signal. 100 volts, then the 1/3 power here, that was like what would represent the 11 dB crest factor speeds that we were talking about before. And the 1/8 power is what represent like the 15 dB crest factor speeds that we were talking about before. So we would expect the system to achieve, for us, 1/8 power in the linear region. So first system, as I said, this is the system that once it's fully loaded has a drop in speed, doesn't achieve the 1/8 power. Well, you can say that, well, that system is wrong. No, it makes sense because we are expecting this bar to be here. So that means that the red bar needs to be higher. So if the system has just exactly the required headroom, we should never expect the bottom of this graph being here. And that's what we are asking to the amplification systems. We have then this system that he just said, like what he said, achieve 1/8 power in the linear region. We're happy with that. Then we have all of these 4 systems achieve 1/8 power in the linear region and exceed 1/8 power in the linear region. And then we have these other 4 systems that achieve and exceed the 1/3 power. That means that the bottom of this graph is here. So all of this difference of 6 dBs is 6 dBs of the red line going up, at least when using this signal. So what we can take from this graph is there is a big difference in SPL just because of the system that we use when using a STEPA signal between this system and that system. There's a difference of like 6 dBs or more, just depending on the system we use. So let's see what happened with the speech, because at the end of the day, what we are worried about is speech, is what is going to be reproduced by the system. With the speech track, we want to achieve 1/16 power using an 15 dB crest factor, or 1/7 power using that allowed for VA. And then we have like that graph represents the linear, like the linearity, and 100 volts. The first system, again, that's the system that has like that kind of behavior depending on the loading of the channels, doesn't achieve 1/16 power. Well, it should achieve 1/16 power because this signal should fit with the rest of the amplification systems. What we've seen is like, and there is an IS paper talking about that, once signals, they are compressed and they go through any filtering process, the crest factor of the signals tend to go up. It happens a lot with pink noise signals, with artificial signals, with a STIPA signal as well. The effect on speech signals is not that dramatic, but still, it happens. So, in that system, the output signal, because of going through all of the filtering inside the system, might be bigger than the 15 dB crest factor original speech signal, and that's why it couldn't achieve 1/16 power. Then we have this system, achieve 1/16 power. This was the system that couldn't achieve 100 volts, but it can achieve and exceed 1/16 power with speech. Interesting. Then we have these four systems, exceed 1/16 power in the linear region, and then we have these systems, exceed 1/16 power in the linear region, but none of them achieve 1/7 power in the linear region. Well, we wouldn't really expect the systems to achieve 1/7 power in the linear region. That means that they would need more headroom. So it's interesting to see that depending on the signal that we use, the systems kind of like have different headrooms. The same system, depending on the signal, behave completely different. Another interesting point from this graph is we can see a big difference of like 4-5 dBs difference, depending on the system using a speech. That means that it's almost like 4 times the power. 6 dBs, 3 dBs is double the power, 6 dBs is 4 times the power. So we're talking about like 4 times more equipment in a room, just depending on the system we are using. So with all of this data, what do this represent in a real evac scenario? Let's try to put this thing in context. Well, what these measurements represent is like if we had a third-party equipment with signals stored and they are injected into our VA system or into our racks. According to 5839, type B1 systems, they don't require an emergency mic. So they only required a digital voice announcer to operate. So once that digital voice announcer becomes an emergency message, that's an emergency digital voice announcer, what we call an EDVA. So those measurements that we had is like if we had that EDVA is stored in a third-party equipment, is triggered by the fire alarm or whatever system, and then is injected into our systems. That's what those measurements represent. And as I said like before, the objective is when predicting or measuring STI is to correlate that STI result with the real intelligibility when using the emergency mode of these systems, so when using the EDVAs or EDVA, one or more than one. So what we said is like, okay, let's try to put this thing in constants. So we took one system, we took the same speech track, and we said like, okay, our original measurement is a 15 dB crest factor. We store that signal as 1 dVA. Then we use that specific system, the manufacturer recommends some compression settings for the dVAs. We use those compression settings and it ended up in a 11 dB crest factor, a speech track, and then we stored that one as well as a different dVA. And then I said, okay, let's put a little bit let's do it again. Let's put a little bit more further limiting to an 8 dB crest factor. That was just a random crest factor that I decided for this test, and I stored it at another DVA. I trigger the 3 DVAs, and I measure these output voltages. What they represent in dBs, that is easier to see than in voltages, is if we assume that our original speech track is the 0 dB, the compression, as per manufacturer, the 11 dBs, will have a 3 dB higher SPL on site, and with further limiting, we could expect 5 dBs. Again, that's almost like 4 times the power. Obviously, we are talking about compressing speech. Compressing speech will lose quality, but it's like known that everyone is saying like, oh yeah, you can almost destroy speech by clipping it and still be understandable. Well, we didn't do this research, but we found this research quite interesting. This research was done in London South Bank University by Lorenzo Morales, 2014. It's a PhD research. And he compared different clippings on speech on Harvard sentences and assessed intelligibility. We are going to try to focus on 0.5 STI band, that is the target for most of the standards. So, if we look at the 0 dB clipping or 18 dB clipping bars, okay, let's take the 24 dB clippings out. And I'm paraphrasing the researcher on this one. There is no statistical difference in intelligibility between 0 and 18 dB clipping. And the difference of the crest factor of those two signals is the original signal, the 0 dB clipping is 18 dBs, and the 18 dBs clipping is 5 dBs. So all the results that we were talking about before, they would accept more clipping, losing quality obviously, but they still have the same intelligibility. So to show you more or less this, what I did is I took speech track, I compress it as the researcher did, and I end up with a 6 dB crest factor speech track. I'm going to play you this one to see like if...
The birch canoe slid on the smooth planks. Glue the sheet to the dark blue background. It's easy to tell the depth of a well.
Well, as you can see, it's compressed, but all of us understood that track. And let's take the original one.
The birch canoe slid on the smooth planks. Glue the sheet to the dark blue background. It's easy to tell the depth of a well.
Obviously, there is a difference in quality, but there is no difference in intelligibility. So we know that there is no difference in intelligibility when compressing speech, but as we know in 60268, a STIPA signal is affected by compression. But do that effect because of the compression represents the real intelligibility? Well, the same researcher did the test. He applied the same clipping to the STIPA signal, so we can see that between 0 and 18 dB clipping that, as I said, there is no statistical difference in intelligibility, we can see a drop of 0.12 STI. So it's going from a pass to a fail, when in reality, the intelligibility is the same. So, well, what do we do with all of this data? The first thing is we think that EM54 part 16 clause might need to be revised to represent the real usage of those systems. In addition, we think as well that it would be quite interesting to have a speech rating for the amplification systems, as that is what we are going to use at the end of the day. If we agree of having like a speech rating, we need a standard speech track. And if we accept that EDVAs can be heavily compressed and still be understandable with as well lower quality, then that's up to the industry if they accept that lower quality and have a more efficient systems. Then we would need to agree on a dynamic processing for all of the EDVAs, so we can know in advance what kind of crest factor and what we need to assume during modeling, predictions, measurements. Also, if we can heavily compress as well, like the EDVAs, by that much, and as I saw in that graph, we can have like 7 dBs, 8 dBs more of SPL. Are we wasting power because we are designing our systems to be measured with artificial signals and not to be measured on the way that they are going to be used in reality? If we accept that, then we will need to consider that when using a steeper signal or indirect methods, we will need to adjust the SPLs. We would measure one SPL on site, and then we will need to measure the SPL of the EDVA and adjust the levels. Well, 30 minutes, I think it's fine. If you have any questions.
Did you, in the trials did you run everything on mains power, or did you do any of it on battery backup? Because often, you know, one of the realities of the evacuation is that the power's gone and then the whole thing's running on battery. And through some experience, I've seen some systems not really sound as loud running off batteries as they do off mains.
That's
the next three.
Those ones are the next steps. Okay, the first bits is like, yeah, we consider doing that, but that would have like make this investigation. Like we decided to have more systems and try to reduce the scope a little bit. But yeah, that's something that is already in our radar of a possible future investigation. Yeah.
The systems you had which basically didn't make the spec on sine waves, but did on speech, that sounds like a power supply problem to me. The amplifier was capable, but the peakier speech didn't load the power supply as much as the continuous sine wave.
Yes, and that's something that is being accepted by the manufacturers.
Right.
They were quite clear on that one. All of these systems, like the system that has a drop one is fully loaded, it was a power supply problem. The system that didn't achieve 100 volts, that burst mode system, it's because it's a cost thing.
Right.
And that was said in 2017 by one manufacturer here. It's a cost thing, and they assume that they have like a burst. But it seems that it doesn't work with the 1K, but it works with the speech.
Right.
So maybe there is nothing wrong in there. We don't know. It's just like, I'm just presenting the data.
Were all systems using the same amplifier technology? Were they all, or were they different amplifier technology in terms of the class they were using? Were they all class D, or were they?
Except one of them, all of them, they were class Ds.
The one with the smoke came out.
Yes. Yeah, except that one, all of them, they were class D amplifiers.
Class G.
But, sorry?
The one that smoke came out of was class G, maybe?
I don't know, because that's one of the things that...
Like continuous sine, it would work okay with the speech, but it didn't like continuous sine wave.
It is this system, actually.
Yes.
So it actually had more headroom than what we wanted.
Yes.
So it liked the sine wave, but it didn't like how much we wanted from it.
It didn't like it for a long time.
Yeah. So as far as I'm aware, all of them, they are like class D amplifiers. What we didn't go into, that's like this new approach for this investigation. We just look at those systems as black boxes. We spoke with the manufacturers to adjust the gain structures, the internal gain structures, to have what we wanted. So, yeah.
Can I make one comment about the distortion thing? I mean, you presented quite severe clipping, and yes, you could understand it, but you had to make more effort to understand it. Yeah. And I'm just thinking Harvard sentences, obviously done under lab conditions. And you'd never get this through the ethics committee, but I think you really need to test it under panic conditions. You know, the subjects need to be terrified, because I mean that's one of the arguments for maintaining the intelligibility is in general, when you're using a voice alarm system, some of your listeners will actually be somewhat stressed.
Yes.
And they need to be able to understand the information, you know, probably without having to spend much effort on it, so they can, you know, walk safely in the right direction. And, you know, I
completely agree with that.
So
that's the same for any speech intelligence when you're testing.
Well, I realise
regardless of what you're looking at.
Yeah.
It's completely false.
What I've said is completely false.
No. Any speech intelligence testing is a completely false situation that you're actually looking at.
Yes, yeah. Well, that's true.
So it's the same, doesn't matter if you've clipped it or if you've add reverberation to it or noise to it.
If you are more interested on like this research, I could give you like the contact details of the researcher, because it has been only the PhD has been published. It hasn't been published on any paper, this part at least. But we are assuming, I guess, that when we measure intelligibility, we are assuming that people will not panic on an emergency.
Yeah.
It's if that's true or not is I think is like a year ago it was Dr. Cocking, the one that
Chris Cocking from Sussex,
came here to speak like about panicking, and it was really interesting, like because he's kind of like, I think like idea was like people will help other people, and what we understand about panicking maybe it's not panicking, but again that's Any more questions?
Do you have any more questions? Yes, we do, please.
Was it a dry signal going through all of the systems, or was there any signal processing applied, any filtering, any onboard filters engaged?
Within the system, we set up the systems to work non-EQ, and we set up the systems to work in 100 volts mode. Some systems they have, because they work in 100 volts mode, they have a high pass filter, depending on like the frequencies, 80 hertz, lower, higher. Some systems they don't have that filter. That's why we try we configure all of these systems as they are going to be on site, fully loaded when possible, and in 100 volts mode. So all of this investigation started because we used before a 6 dB pink noise signal, heavily compressed. And we put it into a system that was configured to work in low impedance mode. And we had the voltage that we wanted. Then I put that system to work in 100 volts, and we didn't have the same voltage. And I was like, okay, what's going on in there? And that was in Reproduce Sound, I think 2017, when we spoke with Jamie, and she pointed us to an IS paper that is talking about the effect of compression filtering on the signals. Really interesting IS paper. I didn't include it in here because I think it was too much.
Any more questions for Alberto?
Yeah.
I was just going to say, of the low performance system, what was the power rating of that amplifier?
Of the low
performance system?
The one that didn't
meet the criteria for 100 volt.
Sorry.
First one.
First one.
This one.
This one, yeah.
Not this one.
Yeah.
Because when you said low, well, this one, when it's fully loaded, is slow as well. The previous one.
Yeah.
That one.
It was some kilowatts, like 4 channels kilowatts,
But it probably met the specs, didn't it? Because it would have been certified for...
This one is not EM54.
Ah, right.
Okay?
Right.
But it's used in voice alarm applications.
But it has been designed to be used with constant voltage, as a constant voltage amplifier.
It has, and you have the amplifier was, the system was configured to work in 100 volts, so it's designed to work in constant voltage. It's not EM54, but we know that you have some exceptions of using EM54 systems or not, in voice alarm systems or SSEP systems. So we know that this specific system is being used on voice alarm applications. So, yeah. And it says, like, when you read the specs of these amplification systems, it's written that it's a burst mode.
Yeah.
It's not in big letters. It's in a really small letters at the bottom of the page, but it's somewhere there. Okay.
Alberto, would you like to just say a few words about how working with the manufacturers has been, how interesting they found this process with you?
Well, we work, like as I said, like with 8 different manufacturers. Some of them really open. Some of them, like the feedback was like, thank you for the report. We need to figure out this thing. We discovered things that they didn't know. Some of them were really close. So here is the equipment, measure it, that's it. So, but in general, it's been like well accepted by most of the amplifiers. I would say like 80–90% of the manufacturers, that the results that we presented here. Yeah.
Thank you. I just wanted to make reference to the fact that the manufacturers have been very much involved in the process, mostly, and so nobody's equipment has been tested in a way which they haven't been involved in, really. Yeah.
But did they believe those?
Sorry?
Did they believe you? Because I've had manufacturers that patently just don't believe the results that you give.
Well, in that case, what I did is I present those results to them. I send them an internal report, only use quick thing for them. And if they didn't believe that, I asked them, like, this is the process I'm using. We send them the handbook that we have to do all of these measurements. They review that, they accept that it was correct. And then I ask them, can you send me your config file? So I measure this thing in the way that you think that is correct. So I'm not doing anything wrong in the configuration, because, well, these systems, they can be configured like so many ways. And I measure them again. And I mean, what it is what it is. What is said in the sound level meter is like, there is no discussion about that.
I don't disagree.
So, but in general, like I said, like 90% of them, they've been really receptive and open and friendly with, like.
Yeah. To the extent where we had one guy pretty much living in our office, didn't we?
Yeah.
He didn't want to leave. He was just having a lovely time.
Yeah. 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 And that specific manufacturer like discovered things that they were not aware of, problems with internal gain structure. They didn't know that. And they were like, whoa, yeah, we are going to put our team to work on that. Because
You could argue that's a really positive thing to learn.
Absolutely.
Yeah.
Absolutely.
yeah, they were, that's the thing, like most of them, they were really happy and friendly to open and saying like, obviously all of this data is like no names because everything is, but.
Yeah, we're very grateful that they were willing to give us the equipment to even investigate this with, because we obviously identified a serious issue in terms of our workflow, but also it's an industry problem at this point that needed solving. And Alberto, I think you haven't really spoken much about having to develop even the methodology to do the testing, which has been an intensive part of the work that you've done.
Yeah,
So
well, I took that bit out of the presentation, but yeah.
Any more questions for Alberto?
Can you just go back to the last SDI slide where you actually reduced it?
Like the linearity or the...
No, the actual
SDI.
steep
Final
one,
slide.
where you actually showed it reducing.
Yes.
That one.
Well, if you want, I can put that one. That one is with like different SDI targets.
Yeah.
Okay, well, or this one is the same.
That was, yeah.
Yeah.
No, you took one further on from that. I thought.
No,
Oh, okay.
that was
Fair
it.
enough, that one. Okay. So I just didn't get the last grey.
The last grey one is that one. I hide it because there is with the 24 dB clipping, we can see a difference in intelligibility. And the average crest factor of those Harvard sentences, there were 3 dBs crest factor. It's, well, a hell lot of clipping. So that's why I didn't consider it to include it in this piece. So
Trying to relate speech and steeper is incredibly difficult. I mean, I don't disagree with the results. I'm just wondering what we've actually measured.
Well, in terms of what I heard, can I just a comment was, okay, the change in intelligibility, I think, was more than the measured intelligibility change with the Harvard sentences.
yes,
Right,
yes.
because,
Well, so the
I mean,
change in
very
STPA
nicely
was more.
played
Yeah.
the more heavily clipped one first, so we didn't have anything to go on, and I definitely missed parts of the words, even in the Harvard sentence. And yeah, I could have worked out what it should have meant, but
Yeah.
again, you know, when you're trying to think, oh God, the lights have just gone out, and it's emergency lighting, and I'm trying to go
Yes.
to the exit,
Yes.
maybe that's not the time you're going to think that out.
I think that, Alberto, isn't that why you chose to play it that way round?
Yeah, that's why I chose like to play like first the clipped one and then the original
It's
one.
interesting.
Yeah.
I think the STI overestimates the degradation, but the Harvard intelligibility one maybe underestimates it a bit.
That's as far as I know, this research was done like in a listening room. All of the it was contaminated with reverberation and noise.
Yeah.
To achieve that 0.5 STI. But as you said, like no panicking situation,
Yeah.
nice and warm in a room.
Sentences with
Yeah.
full context and everything else, because it's
Yeah.
a sentence.
The other thing to mention is I said that the average crest factor of those Harvard sentences with 18 dBs of clipping was 5 dBs.
Right.
That's an average. Some of them they were 3, some of them were 7. So it's a big range as well of that on that crest factor.
Well, thank you so much, Alberto, for presenting the extension of the work that you'd started a few years ago. Thank you also for the questions and for answering the questions. We'll let you off the hook now. That's 15 minutes of questions. So thank you, Alberto.